Have you ever marveled at the silent strength that holds our world together? The invisible skeleton of every skyscraper, the vital core of your luxury vehicle, or even the simple cast iron skillet that has lasted generations. Iron is so deeply woven into the fabric of our everyday lives that we often forget its presence. But what if I told you that every ounce of this metal was forged in the heart of a dying star and delivered to us through a planetary catastrophe billions of years ago? Let's dive into the fascinating process of the cosmic and earthly birth of iron. This is your nerd friend. Deep inside every massive star, fusion forges elements in a relentless climb up the periodic table. But this journey has a summit, the binding energy peak, where the rules of physics draw a hard line. Here, Iron 56 stands as a cosmic gatekeeper. Its nucleus holds each proton and neutron with a grip so tight that no further fusion can release more energy. The binding energy per nucleon for Iron 56 is about 8.8 million electron volts, the highest of any stable nucleus in the universe. Lighter elements like carbon and oxygen fuse together and give off energy, fueling the star's brilliance. But once the core is stacked with iron, the game changes. Fusing iron or anything heavier does not pay out, it demands energy instead. Nuclear astrophysicist describes it this way: a star is like a cosmic engine, burning through its fuel to stave off collapse. But when it reaches iron, that engine stalls. It is as if nature itself has set a limit. No more free energy to be made. The final act in this stellar drama unfolds in the heart of the star's core, where silicon burning races through a web of nuclear reactions. Alpha particles, helium nuclei, are captured by silicon and other elements in a frantic chain, building up to nickel-56. This isotope is unstable with a half-life of just over 6 days. It decays to cobalt-56, which itself decays over 77 days, finally settling into stable iron-56. Each decay step releases energy, not just inside stars, but lighting up the afterglow of supernovae across the cosmos. At this microscopic scale, the fate of a star and the cosmic birth of iron are sealed. The core, now packed with nickel and iron, can no longer resist gravity's pull. What happens next will reshape entire galaxies. But it all begins with the iron summit, where the universe's most stable nucleus first appears. Iron's story doesn't end in the heart of a dying star. It explodes outward, scattered by some of the most violent events in the cosmos. When a white dwarf star in a binary system tips past the Chandrasekhar limit, about 1.4 times the mass of our Sun, an unstoppable chain reaction ignites. Carbon and oxygen fuse in a runaway thermonuclear flash, tearing the star apart in a Type 1 supernova. In a single moment, centuries of quiet stability are replaced by chaos. The entire white dwarf is unbound, hurling its contents into the galaxy at thousands of kilometers per second. Each Type 1 supernova forges and ejects nearly 0.6 solar masses of iron, enough to build the steel frames of millions of skyscrapers. This is not a slow trickle, but a galactic downpour. The blast wave plows through interstellar clouds, seeding them with iron and other heavy elements. Over time, this material will drift, cool, and gather, setting the stage for the birth of new stars and worlds. Astronomers track these cosmic forges by their unmistakable fingerprints. Early in the explosion, silicon atoms absorb light at a wavelength of 6,150 angstroms, a telltale sign that marks a Type 1a event. Months later, as the supernova fades, the spectrum glows with broad iron lines, revealing the true scale of the metal released. This is how iron leaves its stellar cradle, not as a quiet deposit, but as a shock wave, an elemental broadcast that echoes across the galaxy, shaping the future of solar systems yet to come. Every piece of iron on Earth carries a memory, a signature, etched not just by cosmic violence, but by the quiet chemistry of the early solar system. Meteorites, those battered messengers from the asteroid belt, reveal a split older than the planets, non-carbonaceous chondrites from the inner solar system, and carbonaceous chondrites from the outer reaches beyond Jupiter. The difference is not just in their minerals or their water content, it is written in their iron. Earth's iron matches the non-carbonaceous group almost perfectly. The key lies in iron 54, an isotope ratio so precise it acts like a barcode for planetary ancestry. Earth, the Moon, Mars, and Vesta all share this inner disk fingerprint. Carbonaceous chondrites, by contrast, show a heavier signature, a mark of distant, colder regions where ice and organic molecules gathered. The numbers are stark. Earth's iron 54 sits at 0, end-statite chondrites within a hair's breadth, ordinary chondrites close behind. But the outer disk meteorites drift higher, their iron 54 values offset by more than 0.4 of a part per thousand. This is not just a chemical curiosity, it is proof, etched in iron, that the building blocks of our planet were sifted from the inner solar nebula. The iron in every bridge and every drop of blood was sorted billions of years ago by the invisible hand of the protoplanetary disk. The evidence is clear. Earth's iron did not wander in from the outer solar system. Its story is local, born from dust and gas that circled close to a newborn sun. Iron's journey through the cosmos finds its next great turning point beneath the newborn Earth's surface. Imagine a world just formed, battered by impacts, awash in molten rock. In this crucible, iron, once scattered by supernova, faces a new ordeal. The early planet's heat, stoked by radioactive decay and the violence of accretion, melts both silicates and metals. But iron is heavier, denser, and it begins to move. Gravity takes hold and molten iron starts to percolate downward, weaving through a tangled matrix of silicate crystals like rain seeping through fractured stone. Sometimes droplets merge into rivers, pooling into vast metallic lakes that plunge toward the center. Other times, whole blobs of metal, diapers, descend in slow-motion avalanches, dragging heat and lighter elements in their wake. This descent is not gentle. As iron sinks, it releases a torrent of gravitational energy, enough to melt the entire mantle, enough to turn the planet's interior into a churning ocean of magma. In less than 100 million years, Earth's core is born, a sphere of liquid iron and nickel thousands of kilometers across. The planet is forever changed, dense metals locked away at the center, lighter silicates rising to form the mantle and crust. Most of Earth's iron vanishes into the depths, leaving only a thin residue behind, just enough to shape continents, to feed ancient bacteria, and one day to fill the veins of every living thing. The iron catastrophe is not just a story of loss, but of transformation. What remains at the surface will become the foundation for all that follows. Beneath the world's oldest continents, ancient bands of iron lie hidden, rusted red, black, and silver, layered like the pages of a forgotten diary. These are banded iron formations, stretching back more than 2 billion years. Each layer is a silent witness to a time when Earth's surface chemistry was rewritten by life itself. Peering through the lens of deep time traces these stripes across cratons in Australia, South Africa, and North America. The secret is in the layering. Iron dissolved in the primordial oceans, delivered by volcanic vents, drifted unseen until microscopic architects, iron-oxidizing bacteria, began to work. They breathed out oxygen, not enough to fill the sky, but just enough to rust the iron in the water. Drop by drop. Over millions of years, Hematite and magnetite settled out, painting the seafloor in alternating bands. These ancient deposits are more than ore. They are the fossilized fingerprints of the Great Oxygenation, the moment biology and geology met to forge the raw material of civilization. In the hands of metallurgist Ana Torres, the journey from rock to skyscraper is a trilogy of transformation. First comes extraction. Miners unearth veins of hematite and magnetite, ancient ores born from seas rusted by primordial life. The real alchemy begins in the blast furnace. Here, crushed ore meets coke and limestone at temperatures above 1,500 degrees Celsius. Carbon strips away oxygen, freeing molten iron that pools at the furnace's base, heavy and impure. This pig iron, rich in carbon, is only the beginning. Next, the basic oxygen process takes center stage. A lance delivers pure oxygen into the molten iron, burning away excess carbon in a controlled blaze. Impurities vanish as slag, leaving behind tough, malleable steel. For recycled metal, electric arc furnaces offer a different path. Scrap steel is melted by powerful electrical arcs, transforming the old into the new with remarkable efficiency. Through these phases, iron's cosmic legacy is reshaped by human ingenuity, returning star-forged metal to the world as bridges, rails, and the invisible skeletons of cities. Iron's reach extends far beyond the visible world of bridges, rails, and towering cities. Deep within the planet, rivers of liquid iron swirl in the outer core, their restless motion generating a vast magnetic field. This invisible shield, the geodynamo, stands between Earth and the relentless solar wind, deflecting charged particles that would otherwise strip away the atmosphere and scorch the surface. Without this planetary armor, oceans would vanish, and life as we know it could not endure. But iron's power is not just planetary, it is personal. Every breath depends on a molecule shaped by ancient stellar forges, hemoglobin. At its heart sits a single iron atom, able to bind oxygen through a reversible dance of electrons. With each inhale, iron captures oxygen in the lungs, releases it in the tissues, and returns for more, cycling through the body in silent service. The same element that shields the world also carries life's essential spark, linking the fate of a planet to the pulse of every living cell. Every beam, every heartbeat, carries a legacy forged in stellar cataclysms. Iron is not merely Earth's backbone, it is the cosmic thread that binds all life and industry. When you grasp steel, you hold the aftermath of supernovae. What else in your world hides such an ancient universal inheritance?